So this lecture on stationary distributions of different that null recurrent and positive recurrent state and irreducible positive recurrent Markov chain, etc. So before doing that, we have to know one important theorem without proof, that is called bounded convergence theorem. This is very important. Bounded convergence theorem. This is basically an important theorem in real analysis and measure theory also. This is bounded convergence. We state here without proof. Bounded convergence theorem. So let A depends on x, like is a function. So x belongs to a state space. Be non-negative numbers, real numbers, actually, non-negative numbers. Non-negative means it is real. Once I say it is non-negative, that means it is real. And having finite sum, the sum is finite. That series sum is finite. And let Bn is another sequence of function that x belongs to this script S, that state space. And for n greater than or equal to 1, be such that Bn, that mod value of Bn less than or equal to 1 for all x belongs to the script. So Bn is such a sequence of functions so that mod value is less than or equal to 1 for all x and for all n and for all n also. And this take the limit of n tends to infinity of Bn is just Bx. That take that limit as Bx is bounded and non-negative numbers. Bn may not be non-negative, so Bn may be negative. So this sum is limit is exists. We assume that limit exists and limit is Bx for all x, that function. Then if this is true, then what happens? Then limit n tends to infinity Bn into Ax, that's sum over x. This is just sum over Ax into, so that means the limit and this summation can be interchanged. So it's just limit is inside, and it after taking inside, that limit of Bn is Bx. So limit and summation can be interchanged. So for infinite case also, if this condition holds, that sum over that Bn is sum over An is finite and A is finite and Ax is non-negative, and Bn x is mod value is less than or equal to 1. If this condition holds, then this limit and summation can be interchanged. So we omit the proof. Now we have this important result on the basis of this. So what is the result? The important result is, let pi be a stationary distribution and let m be a positive integer, m be positive, so natural number, so it belongs to natural number set. Then sum over all z, that pi z, that stationary distribution is also initial distribution, and pm x to z to x at m step transition function, that sum is pi x. This implies 1 by n, sum over m equal to 1 to say n. Take the sum over that, and then again sum. You take the sum of the left hand side, that is phi z or z, that Pn zx is, so it is a just x m equal to 1 to n, so it's down right side is just pi x plus pi x, so m times n times, then divided by 1 by n, so it is average is again pi x, because pi x is constant over n. So that's why the right hand side is pi x and left hand side is this, and that implies actually sum over z pi z, that is you just take the inside, you take the sum, there is finite sum, so you can put inside, and that is gn zx divided by n, that is pi x for all x, that is true for all x belongs to script s. So next important theorem is, let pi be a stationary distribution and if x is a transient state or a null recurrent state, transient or null recurrent, something transient or null recurrent is very closed. We see earlier also in earlier lecture some theorems, transient and non recurrent is very close actually. The important part is whether it is positive recurrent or not. So non recurrent state, it is true, this was very similar. The result true for transient is also true for null recurrent, that pi x equal to 0, that stationary is pi x equal to 0, this is a stationary. If x is a transient or null recurrent, that pi x must be 0. So that starting initial probability start with the probability must be 0, initial probability must be 0 for the transient and recurrent state, null recurrent state. So what is the proof? Proof is just coming from the previous thing. So limit n tends to infinity, gn zx by n, it is 0. You know that is 0 for transient and non-recurrent state. So it is 0 for that, you just multiply it by pi z. So once you multiply by z, then also it is 0. Then it is also 0. Now take the sum. Take the sum. This is also 0. Now you can interchange that too by this bounded convergence theorem. So using bounded convergence theorem, you can interchange that this too. So it is just you just put outside the limit, outside the summation. So n tends to infinity, sum over pi z gn zx by n. This is 0. But what is this? This is pi x. This is pi x. This part is pi x. This is pi x. So here, from this is pi x. So what happened? So limit of pi x is again pi x. The limit of n tends to infinity, pi x must be pi x. There is no such n here. So pi x equal to 0. So this prove the result that pi x equal to 0 by the previous argument and this bounded convergence theorem. So that's why it's very important. Now one important note is this: a Markov chain with no positive recurrent state. So if there is no positive recurrent state, then what happens? Then it can't be. There should not be any stationary distribution, because otherwise all the value of pi x is 0 for all x. It can't be true, because once it is stationary, the sum must be 1. So if for all x it is 0, how can be the sum is 1? So if there is no positive recurrent, there is no such stationary distribution. Positive recurrent state, Markov with no, does not exist, does not have any stationary distribution. So if there is no positive recurrent state, then stationary distribution does not exist, because then pi x is 0 for all x. It can't be true for any distribution. Pi x cannot be true for 0 for all x. But if some positive recurrent state exists, is stationary distribution exists? That's the question. So we have the next theorem. An irreducible positive recurrent Markov chain has a unique stationary distribution. So that's the important part. So if this is irreducible positive recurrent state, that means every state is positive recurrent and it is irreducible, then it has unique stationary distribution. And that distribution is given by, distribution pi is given by the following relation, that pi x is equal to, pi x is 1 by mx. So this gives the unique stationary distribution. So two things must hold: it must be irreducible and just positive recurrence. So one state is positive recurrent, then every state is positive recurrent, because it is irreducible set. So what is the proof? Proof is slightly long. It's not non-trivial proof. So first we have this limit n tends to infinity, gn zx divided by n, that we see earlier in lecture, that this is rho zx divided by mx. And rho zx is 1 because it is positive recurrent, it's recurrent state. So this is for x, z belongs to script a. So this is 1 by mz. Now suppose pi is a stationary distribution. Suppose pi is a stationary distribution. Then by bounded convergent theorem, what happened? That by bounded convergent theorem, what we get? We get by bounded convergence theorem, that pi x is the limit n tends to infinity, that sum over all x, all z pi z, that is pi x into that gn from x to z divided by that n. So this is pi x by bounded convergence theorem. We prove it. We have proved it. So it is 1 by mx sum over pi z, but this is a stationary distribution, so it is 1 by mx. So that means if stationary distribution exists, then this is true. Pi x is 1 by mx. But we don't know whether it exists or not. We have to show that it exists. The stationary distribution exists, and this is unique. So next we show it exists. If it exists, then it must be 1 by mx. So how do you show that this is if it exists, then it is unique, 1 by mx. So to show this is a stationary distribution exists, one more thing we have to show, that this must be distribution. That means sum over pi x must be 1. That we have to show. So we have to show two things. Sum over pi x is 1, number 1. That is sum over 1 by mx is 1. That means pi x is a distribution. And we don't know whether it exists or not. If it exists, then must be that 1 by mx. That is unique. So we already proved the uniqueness. If I show that this sum is 1, then we prove that this is unique. But we have to prove that this exists. This such a distribution exists. So what we have to show that this is a stationary distribution. So we have to show one first thing, that sum over 1 by mx, that pxy must be 1 over my. That is the definition of the stationary distribution. If such a distribution is stationary, then this must hold. So to show this stationary, this is a stationary distribution, we have to show that this number one, and once we show that this is number one hold, that means this is a distribution and this must be a stationary distribution, must be that, so it is unique. So one more thing we have to show, that sum is must be one. So these two things we have to settle down. So once we these two we shown this these two things, done, we are done. So first, one by one, we have what? We have this sum over all x, p m z x is 1. We know that it is 1. It's true for all m and z. Now, what happened? Then take the sum over that, and that n, and there is no such this thing, the sum over x. Then so right hand side is just 1, so it is sum over n many ones, and then 1 by n, so it is 1. Now you can interchange this to by bounded convergence theorem. You can interchange that too. So once you interchange, it will give g and x here, because the sum 1 by n sum over m equal to 1 to n, that p to the power m zx, that it is not p to the power m, it is actually, it's not the pzx whole to the power m. It's actually p to the power m is a m stress transition function. It is not pzx whole to the power m, not that. It is just a m stress transition function divided by that n is equal to 1. Now we also have we have this thing, and we also have that part also. Sum over all x p m zx and then p the transition function from px to y, that is, we know this is p1 plus m plus 1, and that is by definition of transition function. Now from that we implies that what we again we take the average of all these things, what m equal to 1 to n, we get what? We get that right hand side is just 1 by n, sum over m equal to 1 to n, m plus 1 step transition function from z to y. Now again, you just bounded convergence theorem, you can just put inside that summation. Then sum over x is this, what? This is g n zx. We know this is g n zx divided by n into p x y, and the right hand side is what? This is g n plus 1 zy by n. And important thing is there is you should take somewhere 1 to n plus 1. Somewhere it is actually, if you start from what? If you start from 1, that means it is p2. The summation must be from 1 to n plus 1, but here summation is from 2 to n plus 1. If you put m equal to 1, it is p2. M equal to p3 up to n, m equal to n plus n. We need that from 1 to m plus n. So that p1, that p zy is not here. So it is there. So we have to take the minus of that. So one term is absent. So one term is absent in the right hand side in gnx. Gn plus n plus 1 zy is actually sum over m equal to 1 to n plus 1 pm. So that for the all the p2 p3 these are exist in this summation, but p1, that is p does not exist in this summation. So that's why we take the minus. Now there's, can we take the limit? Yes, we can take the limit. Limit n tends to infinity, sum over this. But the question is, can we interchange these two? Can you interchange this limit and summation? Now if the summation is a finite sum, then it is, we are true. This summation is, if you take the limit of that, the right hand side, what is this? The right hand side summation is, this part is 0, p zy by n, that tends to infinity is 0. It is just n tends to infinity, g n plus 1 z this by n. So we have this result, that number 1, we got this result, this 1 by mx, that is summation 1 by mx, then summation 1 by y. That is, this limit is actually, that part is just, limit of that is just 1 by mx, then px y, that summation is there. So you just interchange the summation. If okay, if script s is finite, if it is finite, then what happened? We can interchange that. Then it have this limit n tends to infinity gn zx by n. This part is, this limit is actually, and this limit is, we know this limit is 1 by my or m. Yes, it is 1 by my, and this part is 1 by mx. 1 by mx. This part is 1 by mx. So done. So if s is finite, it is easy to prove that. But if s is infinite, then we need the bounded convergence theorem. So if whatever, if f is infinite now, so we have to prove for the infinite case now. So let s is infinite. So we can't interchange directly that. Now, okay, here BCT is not hold. Note that we can't use bounded convergence theorem. Note that BCT does not hold here. Is not applicable. What is not applicable? Because for BCC, what happened? That sum must be less than equal to 1. And that sum may not be less than equal to 1. That sum. There's the mod value of that summation b, that bnx, the mod value of bnx must be less than equal to 1. But here may not be true. That value may not be less than equal to 1. That's the problem. 1 by mx may not be less than equal to 1. So BCT is not a hold. Other thing is okay. That this is non-negative, that part is okay. Limit is exists, that's okay, but that may not be less than equal to 1. That is, so BCT does not hold here. So what we have to do, something tricky. So let script S1 is another finite subset. So since when we know what is true for finite, we take a finite subset, be a finite subset of S. We take a finite subset of S, script S. And in that case, this is true because it is finite. So this is less than equal to 1. So if it is sum over all x, then it is 1. So you take less than equal to 1. So that implies actually 1 by s belongs to that. Then you can take the limit, since now S1 is finite, so you can take the inside. Now if you take the limit, you can put in the limit inside the summation. So limit of that GNS is now 1 by mx. So this is true for S1. So any finite subset. That means it is true for any finite subset. That means what happens? That means so now x belongs to S 1 by mx, that is also less than equal to 1 because it is true for all finite set. Now it is true for the whole set also. Now similarly, what happened? Similarly, we can show that 1 by using that finite case. this is less than or equal to 1 by my. So for finite it is less than or equal to 1 by my. So since it is true for all finite set, this is true for that whole set also. But we have to prove the equality actually. We have to prove the equality. So we prove that less than or equal to 1 and less than or equal to 1 by my, and this is true for all y. Now this implies, now take that, or again take the sum over all this. Now right hand side is bigger than that, so this is bigger than 1 sum over y. Then take the sum over x, 1 by mx, transition function from x to y. Now you can interchange that. Now you can interchange this thing, sum over y. Then what happens? Then it is, this is a 1. Remember, this is 1 from x to y. From all y, this is 1. So this is, but sum over y equal y 1 by my is actually sum over m 1 by mx. This was same thing. It's just y. We can write anything, x, y, anything. Sum over I equal to 1 to n ai is same as sum over j equal to 1 to n aj equal to sum over k equal to 1 to n ak. So since this are equal, this every step is equal. That means this step is also equal. That means what happened? That means this step is also equal. This is an equality hold here. So that means this equality hold. Now, how does this equality hold? Now, each term is less than or equal to this, but the summation is equal. That means that if I have this part that ai is greater than equal to bi, and sum over ai is equal to sum over bi, that means all ai must be equal to bi. Otherwise, if one ai is strictly greater than bi, then summation cannot hold. That means each thing, this part is equal to this, and that implies each of this sum over x 1 by mx pxy is equal to 1 by my for all y belongs to this. Now we have to show the sum over that sum is 1. To show that, what we show, we set a c, number c, that is 1 by sum over 1 by mx. You set this value as c, and you take a function fx c by mx, c by mx. That means it is what is c by mx? That means if you have 1 by mx, then divide by sum over 1 by mx. Now therefore what happened? Therefore sum over x fx, that is 1, and sum over x fx, if we multiply by pxy, that is again fx. We already proved it in the previous. Prove it here. Already proved the first. Actually, we have proved the first number 1. That first thing. That part we already proved. So to show two things, we prove the number 1, and using that number 1, we are going to prove the number 2. So this is fx. Again you take the summation. So this somewhat this is 1, and this somewhat this is, so that means what? That means fx is a stationary distribution. The sum is 1, and sum over fx is 1, and that fx is just a summation fxp. That means the fx is stationary. Therefore, fx is a stationary distribution. But we already proved that once it is a stationary distribution, that must be 1 by mx. Therefore, that fx must be 1 by mx. And once this fx is 1 by mx, we assume that fx is c by mx, and from that we imply that c equal to 1. And since c equal to 1, that means summation 1 by mx this is 1, because if c equal to 1, this is 1. So this completes the proof of that stationary distribution exists and it is unique, and that is actually 1 by mx, pi x equal to 1 x. Next, one corollary of that, an irreducible Markov chain is positive recurrent if and only if it has stationary distribution. So if it is a positive recurrent, then it has a stationary distribution. It must be, first of all, it must be irreducible. If it is not irreducible, we don't know what happened. If Markov chain is irreducible, then positive recurrent, if stationary distribution exists, then it is positive recurrent, and if it is a positive recurrent, then stationary distribution exists, and if stationary distribution exists, that must be positive recurrent. Because if stationary distribution exists, then it can't be any other than positive recurrent. Because since it's irreducible, either the all states are positive recurrent, or all states are non-recurrent, or all states are transient. But we already proved that for the null and transient state, that stationary distribution does not exist. So once the stationary distribution exists, that must be positive recurrent. And next, in the previous theorem, we proved it that if it is stationary positive recurrent, that stationary distribution exists. So therefore, it is if and only if it has a stationary distribution. So once this Markov chain is irreducible, that every state must be positive recurrent. Now the question whether if it is the stationary distribution reducible. So we know that then it is a union of some irreducible set. Next we will see that part. Then what about for general Markov chain? If it is not irreducible, then this every irreducible part has different stationary distribution, and then the stationary distribution is not unique actually. So before that, we give some example that irreducible birth and death chain. So one irreducible, take an irreducible birth and death chain, birth and death chain on non-negative integers, non-negative integers. So on a natural number union 0. So all non-negative integers. Number one, we know that when it is positive recurrent, the chain is positive recurrent, positive recurrent if and only if we know that sum over x equal to 1 to infinity, that sum must be finite. P0 dot dot px minus 1 divided by q1 dot dot qx, that must be less than infinite. And we know that the chain is transient if and only if this x equal to 1 to infinity, that sum now sum is from q1 q2 dot dot qx divided by p1 p2 dot dot px. So that sum is finite. Then it is transient. And what about null recurrent? The chain is null recurrent if and only if two things must hold. Number one, that sum over x equal to 1 to infinity, starting from p0 dot 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 px minus 1 divided by q1 dot 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 qx, that is infinite. So positive recurrent, this is finite, null recurrent is infinite. And that part also, the next part, x equal to 1 to infinity, that q1 q2 dot 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 qx divided by p1 p2 dot 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 px, that is also infinite. It is finite for transient and is infinite for non-recurrent. Next thing, there is one corollary. If a Markov chain having the finite number of finite number of states is irreducible. So having a finite number of states is irreducible. So since it is a finite number of states and it is irreducible, and that means it is a finite number of states, means every state must be positively recurrent, because there exists at least one positive recurrent, and once there is at least one positive recurrent and this is irreducible, therefore every state is positive recurrent. For finite, there must be at least one positive recurrent state. So irreducible, then it must be, if it is irreducible, then that must be positive recurrent, and it has unique stationary distribution. So once this Markov chain has a finite number of state space, the state space is finite and it is irreducible, finite state space and irreducible, then that has a unique stationary distribution. Now next corollary is this: let xn n is greater than or equal to 0 be an irreducible positive recurrent. Markov chain having stationary distribution pi. Then what happen? Then for all x belongs to script s, that limit n tends to infinity, that nx by n, what is nx? The number of visit to x during the time n. Nx equal to pi x with probability. That is the stationary distribution. So what is mx? Where mx is nnx is the number of visits to x during time m equal to 1, 2, dot, 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 n up to n. Now from that we can easily prove this important result, that note infinite Bernoulli terms. So there is infinite Bernoulli terms is a Markov chain. We know this is a Markov chain. And from what is actually this? The stationary distribution, that limit of n x by n, that is a stationary distribution, that in limit n tends to infinity. What is this meaning? Number of, say it is a visit x is head. So number of x in n times n. So for n toss, how many number of head? That limit is equals to the probability of that x, that head, and that is a strong Laplace number. And this is exactly the strong Laplace number with probability 1. The strong Laplace number say number of 1 divided by n, number of 1 in n tosses divided by n means 1 means head, and 1 means head by n, that limit is tends to that probability of head, the stationary distribution with probability 1. Then that is a strong Laplace number. Strong Laplace number follows from the above corollary. Follows from the above result. So here we actually prove the strong Laplace number. So we stop here. This lecture, this video stop here. Next we the remaining part is the irreducible chain. The reducible chain. What happens if the reducible chain, for the reducible chain, we have some irreducible component, and then we have this result. Using that result, we have some result on that reducible chain. So we need one more lecture for that. So stop here now.